All right. Thank you. Thank you for introducing. So my name is Doowon Kim, and I'm a PhD student at University of Maryland. Today I'm going to talk about the measurement effective revocation process in Windows Code Sign PKI. This research work is done with Bomjun and Christian and Chris and Professor Tudor Dimitraj. So as the nature of software distributed over internet, so we cannot identify the software, the authors, and the software can be tampered. So the code-assigned PKI is a solution to help establish the authenticity of authors and the integrity software. So we know who publishes software, and the software is never altered after sign. However, the PKI is not a perfect solution because we have seen a lot of abuse cases. The first abuse case is Stuxnet. As you know, the Stuxnet is the very sophisticated target attack is signed with a stolen private key associated with the Taiwanese companies. And then the second example is the blank market. In the blank market, in a prior work, we found that adversary trying to purchase the code-assigned PKI, code-assigned certificate in the blank market to hide their identity. So the primary defense against this abuse is the revocation. So all the compromised certificate should be revoked by CA. In a prior work, we found that two of the third compromise certificates not revoked yet. So this is our motivation. So we wonder why are the compromise certificates are not revoked yet. So furthermore, do CA properly understand the code-assigned PKI and do the CA properly revoke the compromise certificate without any mistake. So in this paper, we measure the effectiveness of revocations. So how to revoke the potentially compromised certificates? So we identified 3 steps for effective revocations. The first is promptly discover compromised certificate, and the second step, the CA have to invalidate all signed sample when they revoke the compromised certificate. And the last step, the CA have to disseminate the revoke information for clients. Let's look at the first step. The effective revocation process starts with the discovering the compromised certificate. The CA have to collaborate with the security company to discover compromised certificate. And then after the compromised certificate is discovered, the CA have to start investigation on the compromised certificate. So in this step, we raise the research question is that how promptly do CA discover and then revoke a compromised certificate after they appear in the wild? So in this paper, we found that there is a delay of 5.6 months to revoke a compromised certificate after they appear in the wild. In the second step, the CA have to invalidate every single malware signed with the compromised certificate. So this is the main difference from the TLS because in the code-assigned PKI, one certificate can be used for sign as many the samples as the publisher wants. However, in the TLS, this is a one-to-one relationship. So one certificate can be used for one domain. So in this step, we raise also research questions. So do CA properly revoke and compromise certificate and then invalidate signed samples assigned with the compromise certificate? In this paper, we found that the CA improperly revoked the 5% compromise certificate, and then another 5% assigned malware is still valid even though certificate is revoked. And then this is a more challenging and critical and the TLS due to the CA have to invalidate every single signed malware when they revoke the certificate. In the last step, the CA have to disseminate the revocation information for the clients. So the first role is they have to maintain infrastructure to be always available for clients. So, and the second, CA must not remove the expired certificate from CLA. This is a main difference from the TLS. So why do not the CA not remove to revoke the serial number from the CLA? Because of the trusted timestamp. The trusted timestamp extends the trust in the program in the beyond the expiration date. So here is an example. If the sample one is properly signed, and then the trusted timestamp before expiration date, and then sample one still valid even after expiration date, even now. So, which means the CA must care about expired certificate. So, in the last step, we raise the research questions that do CA properly maintain the revocation information and disseminate. So, in this step, we found that the CA removed around 300 certificates from the CLL and then improperly maintain infrastructures. So this is also more critical and challenging TLS because the CA must care about even expired certificate. So we identify the 3 steps for effective revocation process, and then we measure effective revocation process. We show that the revocation code sign is more critical and challenging in the TLS. So here is the outline. So let's take a look further into our detail. So in the first, there's 2 challenges in data collections. The first one is a corpus. In a TLS, the certificate can be collected using the Census.io or IPv4 scanning or Alexa 1 million domain. However, in a code sign PKI, the certificate is really hard to collected because there's no tool, there's no methodology to collect a code sign certificate. And the second challenge is we don't know when the certificate are revoked. In a TLS, the CA specified the revocation date at the evocation field in the CLA. However, the revocation field in the CLA can be differently interpreted. So in a code sign PKI, the revocation delay is the date to determine the validity of signed malware, signed sample. So to overcome these challenges, so we come up with this pipeline. So we utilize the data set released from prior work. Also, we collaborate with the Symantec for the data source. So from the data source, so we collect the code sign certificate, and then so we extract the CLA OCSP point from the code sign certificate. However, the CLA can be used for other purposes. For example, the CA use a single CLA for TLS as well as code sign certificate. So we manually filter out the CLA used for other purposes, so which remain the CLA used for only the code sign PKI. So the CLA OCSP point fed into our measurement system to examine the effective revocations. So let's take a look for the result in each step. Recall that the CA have to collaborate with the security company to compromise certificate, and then immediately they start this investigation on the compromised certificate and to revoke the compromised certificate. So the revocation delay should be as short as possible. So what is the revocation delay? Revocation delay is the delay between when the compromised certificate appears in the wild and the date when the compromised certificates are revoked. So we define the TD as the earliest submission date of the vital sorrow, and the TP is the date of revoke when the revoked serial numbers are at the CLL. So here is the result. So here is the result of a revocation delay. So delay was from 1 day to 4 years, and the average is 5.6 months. So we already know that most of the compromised certificate is not revoked in the prior work. However, we can know that even if compromised certificates are revoked, it takes like 5 or 6 months to revoke. So which means the clients remain exposed to this threat for 5 or 6 months. So we wonder why the certificates are not promptly revoked for a long time. Maybe one of the reasons that we cannot observe all the compromised certificates in the wild. So to answer research questions, so we want to measure how many compromised certificates in the wild. So however, we not unable the actual number of compromised certificates in the wild, since we don't have the official corpus of the code sign certificate to cover all the code sign certificate in the wild. So we utilize the market recapture the methodology to underestimate compromised certificate in the wild. The market recapture methodology is to use to estimate the total number of the populations in the population of the wildlife that cannot be observed all the populations cannot be observed. So market recapture in a market recapture, the population can be calculated by 2 samples and then divided by intersection of the 2 samples. So we utilize 2 data sets. The first one is the VitalSolar, the hunting data set, and the second is the semantic telemetry data set. In the VitalSolar, as you know, this is the largest the web service that a lot of malware is submitted to the website. And the semantic, as you know, this is one of the largest company who trying to collect a lot of the malware sample. So here is the result. So the X bar is the period by weeks, and the Y is number of compromised certificate. And the blue bar is indicated that the compromised certificate we actually observed at the union of the semantic data set and the VitalSolar data set. And the blue bar is estimation of estimation of the compromised certificate in the wild. So we can know that on average we can know that the estimated compromised certificate is larger, like 3 times larger than actually observed. So we can know that even larger security company cannot observe the most of compromised certificate in the wild. So this is one of the cause to the long revocation delay. So let's take a look further into second step. The second step is invalidate all signed samples. In this step, the CA should decide the effective revocation date, TR, to invalidate all malware signed with the compromised certificate. So what is the effective revocation date? So what's the revocation date? So in codified PKI, revocation will be made dependent on the specific date, which is the effective revocation TR. The effective revocation determines the validity of the signed samples, and depending on the effective revocation date, the signed sample become valid or invalid. I'm going to give you an example. So here, there's 2 samples. There's a sample 1 and sample 2 properly signed before the expiration date, and then they properly trust the timestamp. And then if the CA, the set the effective revocation date, RTR, and then sample 2 become invalid, however, sample 1 is still valid because the sample 1 signed before effective revocation date. Here's the example. So you can see that serial number is found the CRLS, so which means it's the certificate explicitly revoked and revoked. However, the Windows said that the sample signed with the certificate is still valid because the signing date is before effective revocation date. However, it has a security threat. What if the sample signed before effective revocation are malware? So which means clients are exposed to the security threat. So before the measuring how CA properly revoked, how properly set the effective revocation date, we want to measure the type of the effect, the trend of the type of revocation policies. So there's 2 types of revocation. The first is a soft revocation, and the second is a hard revocation. The soft revocation is already explained in the previous slide, and the hard revocation is that the CA set the effective revocation to issue date. So there is no security threat. However, invalid all benign sample as well. So publisher have to resign their sample and they redistribute it. So here's the result. We found that most of the certificates are revoked by soft revocation policies. And interestingly, some CA set the effective revocation date after expiration date, which means the revocation becomes effective at all. So all the sample, including malware, is still valid. even though the certificates are revoked. So we measure how many CAs improperly set the effective revocation date. So here's the result. The 5% of certificate has a wrong revocation date, and then 5% of certificate signed with this compromised certificate still valid, even though the certificates are revoked. So which means clients remain exposed this secret threat, even though the certificates are revoked. Let's take a look at the last step. The last step is the CA properly disseminate the revocation information to the clients. So there are three rules required for the CA. The first one is specify. CAs must specify CLA OCSP point in the certificate. And the second, the CA is responsible for even expired certificate. And third, the CA properly maintain infrastructures to be always available for the clients. But before talking about our result, so I briefly explained the enforcement in the Windows. In the Windows, the software policies apply for the checking revocation status. So, which means the Windows believe that the certificate is still valid unless the revocation information is available. So recall that, so CA must specify OCSP point or CLS in a certificate. And however, we found that 0.5 certificate has no CLS OCSP point. 86% of them were issued by third party before 2003. All of them already expired. However, malware is still malware signed with a certificate and the trusted timestamp, the malware can be still valid. So because the clients have no means to check the revocation status. Here's the example. This is a sample signed with a certificate that has no CLS OCSP point, but Windows says that is sample still valid because of software policy, and because Windows cannot check the revocation policy, Windows status. So we also measure the unreachability CRLS OCSP point, and the 6% of certificate, 6% of CRLS has unreachability problems, and the 5% of them has a 404 not found error, which means they remove or move the CLS file from another place. And then interestingly, one CLS is taken by a domain reseller. So here's the example. So if we go to the CLS domain, the domain is being sold in the reseller. The price is $1,000. However, the sample signed with the certificate is still valid because of software policy, and since the revocation cannot be checked. So program, from this we can know that program signed with the certificate is still valid due to trusted timestamping and the software policies. And then the last measurement is recall that the CA is responsible for the even expired certificate. So however, we found that 300 certificates are removed the CLS. So we contacted all the CAs to better understand why it happens in the CA. But the one CA responds that they started investigation, they found the problem. And then they fixed the problem thanks to our study. From this, we can know that even CA misunderstood the code sign PKI. In the last measurement is that we presumably believe that the response from CLL and the OCSP point should be the same. For example, if one serial number is found in CLL, the response from the OCSP should be, say, the revoked. However, we found that 90 certificates had inconstant to the response. So all the certificates were issued by GoDaddy in the start field. I think from this we can know that the CA improperly maintained the OCSP point and the CRLS servers. Here's the conclusion. So the primary defense against abuse is the revocations. And then the revocation in the code sign PKI more critical and more challenging than TLS. Because the first is really hard to discover the compromised certificate and the signed sample. And the second, the CA improperly set the effective revocation, which makes the malware stay valid even though certificates are revoked. And then third, the CA misunderstood the code sign PKI and improperly infrastructures to disseminate information for the clients. So which also makes the signed malware still valid even though certificate revoked. So we release our data set at the signedmalware.org, which is the CLA only for the code sign certificate, and we also every day we collect a revocation publication day. You can use this data for your study. Thank you.
Hi, this is Tim Hollowbeek from DigiCert. I think this was an excellent talk, and I look forward to reading the details in your paper because I think there's a lot we could learn from this as part of the CA industry. There are just a couple of things that I wanted to quibble with a little bit that I'd like to point out.
Sure.
One of the things that you're really like, I think, is that CT probably will be coming to the code signing ecosystem pretty soon.
So that is our next project.
Yeah.
So
okay.
I'm gonna working on it.
Yeah, exactly. So that will help out researchers a lot. Well, we should know about all those code signing certificates that are out there pretty soon.
True.
The minimum revocation delay, there should actually be some rules around when revocation is reported, how quickly CAs have to revoke certificates.
Yes, true.
Unfortunately, there is no forum that can make minimum requirements for code signing certificates right now. The CA Browser Forum attempted to do governance reform in order to be able to create a code signing working group that could adopt such requirements. Unfortunately, at the recent June meeting, that effort was opposed by people like Google and Apple. So we would encourage them to reconsider that and allow us to have a forum where we can create minimum requirements for code signing certificates. The other small quibble is you mentioned the one-to-one thing. For TLS, it's not true either. Multi-SAN certificates can have like 500 domains on a single certificate, so you have the same problem with cross-revocation taking out good sites and potential DOSs from that. The best practices for code signing are actually to issue individual code signing certificates for each signature so that you can use your CRLs to selectively take out only known malware and not have to worry about the problems that you mentioned. So that's another very interesting thing. But thank you for an excellent talk.
Thank you. Thank you for very good tips.